So I'm writing a compiler, and currently I'm working on generation of an intermediate representation for this compiler. So there is a pass that generates three address code, and these three address code becomes assembly code in the next pass. The compiler itself didn't have an intermediate representation first. It just generated assembly instructions from the abstract syntax tree. So the first step to support an additional pass was just to copy assembly instructions into three address code. So basically assembly was kind of three address code, and then it was copied to a separate pass, and this pass was adjusted afterwards. What I mean, so three address code, the basic block of three address code is an instruction, and a list of instructions represent a procedure. In the programming language, each instruction has an operator. It is the kind of instruction or type of the instruction, and it has at most three operands. But instructions can have also less operands or none at all. So the programming language itself called ELNA. Therefore, a lot of data types and procedures have ELNA prefix, and TAC means three address code, and this list, the thing in parentheses are enumerations, and you can see here all the possible instructions in three address code. And the next enumeration is ELNA RTL operator. RTL is basically assembly. The target of the compiler is RISC-V 32 assembly. It's the only supported architecture currently. RTL means register transfer language, but you can see here basically RISC-V instructions. This is the operator, and then here we see also the operands. So each instruction has an operator and at most three operands. And the operands, also we have two operand kinds. One of them is for three address code, and the other one is for the assembly generation for RTL, and they are almost the same. As I said, the first version of the three address code was just assembly, because I generated just assembly at first, but it shouldn't be the case. So TAC operands have also an additional type, stack. Stack means basically it is a local variable, so it just stack offset. But it also has register. It shouldn't have register because free address code shouldn't care about the registers. And actually offset is offset from any register. So it just in assembly it is used basically for instructions like load, for example LW for T0. For T0 would be, T0 is a register operand, and for T0 is offset. T0 is the register and 4 is the offset. Stack is basically the same, but the register is hard-coded, so it's an offset from the stack pointer. So what we want to have, instead of register, we want to have temporary variables in the 3 address code, and all usages of offset we want to replace with the stack. Symbol is a global variable. We need symbols for TAC and RTL, so it remains as it is, and immediate are supported by both instruction sets as well, so it remains as it is. Basically some operations in the RISC-V assembly can have an intermediate, for example add instruction, something like 2, where you have 2 registers and the last operand can be an immediate value. For the 3 address code, this requirement is not that strict, so not only the last operand can be an immediate, but also the first one, and we have to rewrite these free address code instructions later, or free address code doesn't have add immediate instruction at all. You just have add, and basically you can have immediates in any position. For example, free to null, it doesn't matter, so the address code shouldn't be that strict. It should accept any operands at any position, and this 3 address code is then written into assembly, and assembly just generates the required instructions that are supported by the architecture. So what we are going to do, I think we need to introduce an additional type, or we can actually make it a bit simpler. Each register, here are the registers for the assembly. It's one way to name the registers, but there is actually an additional naming scheme in RISC-V. So each register has a name beginning with an X. So 0 is X0, return address is X1, stack pointer is X2, and all registers are numerated with X. We can just replace the register in 3 address code with the number of this register. So basically, if I use T0, I can replace it with X5, I think. Yes. And so we will get rid of registers, but we will have just numbers that represent a temporary variable. A fixed number of temporary variables is enough for the current compiler, so it will be enough to support the current language that is implemented. But later we will need, of course, to generate more temporary variables. But at first we just should separate these 2 stages, 3 address code and RTL, so that the 3 address code doesn't look like a concrete assembly language. Yeah, and we are going to replace these things manually and just test that everything works, and we can look at the compiler itself at the implementation. So let us look for the usages of ELNA TAC operand register. And the first one, it's actually fine. ELNA RTL large operand value, so it converts a TAC instruction into assembly. We can skip these functions. We are going to look at them later. And we are going to start, I think they can skip this function as well. Yes. So the first place is basically here. And ELNA TAC string literal. String literal means that its argument is a string literal, a node from the abstract syntax tree, and we write this node into 3 address code. And here we create an instruction, get address, because all strings are saved in an byte block, and at first we need to get the address of this byte block. And here we see the register usage, and as I said, registers should be used. Here we just replace it with the temporary variable number 5. We are going to save this. So I'm running rake at the bottom of the screen. What it does, it compiles the compiler and gives us an error. I think it should be 4 or 6. Rake is a task runner. This is a Ruby task runner. Then it is 6. It is Ruby task runner. The tasks are written in Ruby, but you can use it for everything. Exactly, it is 6. The reason is basically I'm going to split the screen, and we will work in the top half of the screen, and the bottom I will switch with the position in the source, and we are going to go to these registers again. Basically the enumeration begins with 1, so 0 is basically 1, return address 2, stack pointer 3, GP 4, TP 5, null is 6 exactly. It's therefore we replace it with 6. And I mentioned rake, so I have a rake file that just compiles, runs the compiler itself. The compiler generates assembly code, and assembly code is compiled with GCC after that. So it's not particularly interesting, it's just some helper methods to compile everything, and I suppose we are going to continue. So would be nice to replace register itself, but I think we will just rename it afterwards. So T0, again, this is the same, so we can replace this just with 6. And the same. So these variables, operand type, operand value, and length, they are passed to this function, and their procedure just saves in these variables where it saved the pointer to the string literal. So the caller of string literal can find the pointer to the string node. You can actually see that all types of all variables are word. It's because there is currently no type checker, so a type check is not implemented yet, so there is basically no types or only one type. Everything is word. It will change later, but I'm not so far yet. And the compiler itself is written in itself, and it uses only features that are currently implemented. We can do a test run and see that it still works. This is unit expression, so it compiles a unit expression to free address code. It's basically, we shouldn't replace this thing. The offsets, we will replace with, the offsets later. We will replace the offsets later with the stack variables. So we leave it as is for now. So minus, yeah, it's 6 as well. T1 is 7. So this is probably binary expression, so it compiles binary expressions. The current language does support only simple binary expressions, so basically with two operands, in the sense that no nested expressions are supported. So you can write x equals to 1 plus 2, for example, but 1 plus 3 wouldn't work. It's not implemented yet, so these nested expressions aren't supported in the current version of the language. It's a bit boring, but I suppose we can go from the compiler and just look what it does generally. It is LNTAC call, so it compiles a procedure call to the address code, and it basically saves all arguments. The procedure calls support at most 7 arguments, so more is not implemented yet. It's a bit difficult here. We use basically R0 plus argument count, so because the function expects its arguments in registers from R0 through A7, I think, yes. And we need to copy the stuff in that registers. It should be 11, I hope. Yeah, I should think about better handling for the function arguments, but I suppose it is enough for now as it is. This is 6 as well. Actually, I shouldn't look for the registers. But for this operand register thing, it's actually what we want to replace. So we basically have temporary variables, and these are hard-coded temporary variables that can be used from the address code. It is enough for the current version of the compiler, and we can look later what we can do to support any amount of temporary variables. It was 6, I think, and 11, I suppose. What is this one? It is an assignment statement. So in the first half of this procedure, we compile the left side of the assignment and save it on the stack with a hard-coded offset of 76 bytes. And after that, we compile the right side, load the left side from the stack again, and assign the value on the right to the address on the left. Yeah, it's kind of looks correctly. We should replace this one later. So it would be 11. This is the return statement, so the return statement should save the result in A0, and we do it here. This is again the same thing, but I think it is the caller, so we compile here parameters I think TC parameters, it's called from procedure declaration. Then the function is called, we save past parameters on the stack, so they can be either written in the procedure, and we reference, and from the procedure we reference these parameters from the stack. So it's the same thing basically. 11 plus count and we continue. TC accessor, it's 11. On count register. These procedures generate field accessors for records. On the top of the file where were some records, but the problem is that we can define records. So for example, this ELNA instruction declaration is a record, but we cannot access the fields of these records just because we need a simple type checker for that. That is not implemented. So as a temporary solution, I generate accessors for each field. It's just a procedure, and it starts with the record name, then set or get, and then field name, for example, next. And it gets the record, an object, and the value to set. It is just a temporary solution that was easy to implement, we won't of course replace it later with normal field access, so the fields can be accessed like result next in this case, but it isn't possible currently. So we are going to continue. Register, this is 11. And I broke something. Okay. Let us look what has changed. So it looks fine. This one here we see a 1, but it was replaced with 11. It should be 12. It's probably the wrong function. Oh, no. Working, we'll look once again at it. So I'm working in a virtual machine, so it is just a RISC-V 32 Linux. I used a cross compiler at first, but it was difficult to debug, so I set up a virtual machine, which wasn't easy because there is apparently no Linux distribution for the 32 version of RISC-V. So we are going to continue to look for the TAC operand register, and we skip this stuff. We already changed these things. Okay. 11. Register. I missed this one. And I think that we are done. Yeah. Okay. After that, we can rename register into something else. I would basically suggest temporary. Before they do this, we do git status and this and we save the current version so I can restore it if something goes wrong. So we look for register and replace it with temporary, and after that we replace all occurrences of ELNA TAC operand register with ELNA TAC operand temporary. And it seems to work. And now, instead of registers, we have temporary variables that are identified by a number. The second task will be more difficult. We need to replace these offsets with stack references, and probably we need other instructions to load values from stack and store them to the stack. So we just have to look where this stuff is used. So, and the first usage is here. How many usages do we have? 2, 3, 4, 5, 6, 7, 8. About 8. Load word. So basically what we have here, we save in the previous step we should save an address in a temporary variable, and then we load this address from the variable. Actually what we can do here, we can just look at the step where the load word instruction is converted to assembly. This is this one, I think. Yes. And here we check if our second operand is a stack value, then we load it from stack, but we can add here an additional case and check that if our second operand is temporary variable, then we load the value from the address of this temporary variable. So basically what we want here, we want to replace the second operand with a temporary variable of the same name. If I compile it now, it will crash. Exactly. So basically it generates a run instruction, undefined reference to x5. We can actually probably look at the assembly that is generated. This is build valid stage 16 as LCS X5. Which line was it? 75, for example. Yeah, basically this is this instruction, load word x5 x5, and this is wrong. Actually it should look so. So let us try to fix this. We check that whether our operand type is an ELNA TAC operand temporary, and if this is the case, then we generate an instruction. This is next. I actually not sure. Load word, we get the type, set kind load word on result. So basically I think why we don't set the result here. Yeah, okay. Yeah, I copy a TIC instruction into RTL instruction with memcpi, because as I said at first they were the same, but we really should get rid of this memcpi call. I should probably remember that. No, it wasn't. Basically, we just have to replace one operand in the result. So and here I want to go to this offset, and I don't know where it was, of course. So we just need to replace the second operand in the result. In the result, the second operand should be not a temporary, but an RTL operand of type offset, and its value would be basically the value of the current operand, and the offset itself is 0. So we just need to get the number, get operand value from TIC instruction from the second operand, and I'm sure it won't work. This is actually this should be the other way around. So we get the operand value from the TIC instruction and set the value in RTL instruction. And this works. This is the one case. So we continue to look for TIC operand offset. The next one is this thing. We will just put it into a comment first and replace it with the stack, and stack value is this one and 0. So each operand has 3 values. It is basically operand type, it's the value of operand, and length. Length doesn't make sense for all operands, but it is used sometimes. So if it isn't used, then they pass 0. It is a start instruction. Why it doesn't accept stack? If operand is like 0 is equals 0, then we set next. It is not interesting. But basically we changed the second operand from offset to stack. So what I have to do is basically we almost the same what we did in the previous instruction handling. So we just get the type. I need operand type isn't checked here at all. So we get the operand type of the second operand and save in operand type. So it would be elna TAC instruction get operand from TAC instruction, the operand number 2, operand type. And if this operand type equals to elna TAC operand stack, then we rewrite this operand in the result. So set RTL, we rewrite it to an offset. So elna RTL operand offset. The register is RTL register is SP, the stack pointer, and the offset itself is operand value. Basically it's almost the same. So just operand value, get operand value from the TAC instruction. At an instruction set operand type. So it generates sometimes, oh, it generates the same for the move. Why move? The operand value. The first, we have basically two pointers here. The one is result, and result is probably not the instruction we need. So to load the first value, this function lna_artel load operand value, it loads the value of the first operand and it can generate a move instruction if needed. For example, if the first operand is an immediate, so actually we should change the operand of the next instruction because it is the last instruction we have, yeah, in here, and this is the place where we need to write stack to offset, and it works as expected. So let us look for more cases of lna TAC operand offset. This one can go, and also this semicolon can go. So semicolons are put only between the statements, but they are not required at the end of a statement list. The language itself is basically, the syntax is Pascal modular 2 syntax. My main inspiration was the Oberon programming language. Actually the same thing, and I think probably, no, it's not the same instruction, it's load word. We do the same, we put a comment around it and just try to replace offset with a stack value, and we set the last parameter to 0, and it doesn't work. Okay. This is load word. This is stack. It should actually SP offset. instruction to send operand to stack. What will instruction is the second one, and I check if the second operand is need this on. So if the second operand is stack, then we load the value of the first operand, then we create a new load word instruction. We set operands of these instructions to a register from the first argument. This is fine. And the second argument is basically offset with the value from the first argument load word. Can we do it with an assignment? Probably not. Okay, we can replace this instruction with an assignment. We are looking for offsets, and this is the next case. It is star word. Should be easy, probably, or maybe not. Stack 76 and 0. The same. We had already this one, and we should just replace the second thing with a temporary, and our temporary is 7, and it should just work. And it doesn't, of course. Temporary 7 star word. The second is here, operand type temporary. We implemented it for load word, but probably not for star. And here we look at operand type is the second, so we just add an additional condition where we check if the type is in case C operand temporary. Then we get the value, and we set the second thing to the register. offset this one. This is starboard. This is almost the same, so it's stored temporary. Probably we implemented all cases we need. TAC operand offset, and that was it. So we can go to the operands, and we don't need the offset anymore. Actually, if I remove this, it can still break because of this memcpi. Or maybe not, it works. Okay. Yeah, this is actually what we want. So we have different operand types for the free address code and RTL. Free address code doesn't use the registers directly, just use temporary variables, and we can later improve and don't use the hard-coded numbers for temporary variables, but just use any amount of them, and we have stack variables, basically local variables of a procedure. We can do a final test. Basically, my compiler consists of multiple stages, so each stage adds additional features to the compiler, to the previous stage, but the compiler is written in itself. The first stage was written in assembly. So it is first version of the compiler, 1000 lines of assembly. Basically, it's not a proper compiler, it just reads itself line by line and outputs itself again. If you look at the second stage, it's almost assembly, but there are some language constructs already. For example, there is already support for procedures, but only with one argument and gotos. Yeah, for example here. And all procedures had to start with an underscore. It's not the case in the last stage anymore, because the parser can now distinguish between procedure calls and variable assignments and alike. Yeah, and we still can compile all stages. So if I do reg clean default, it will compile beginning with the first stage, so with assembly, and compile the last stage then. And one can see that the compiler gets slower and slower because a lot of implementations are a lot of things are natively implemented, so there are definitely some things that can be done better.